Dear students, welcome and thank you for tuning in to this video of Statics and Dynamics with me, Dr. Loay Al-Zube. We are still talking about friction. In the previous video, we talked about what friction forces are, and we have explained what is static friction and what is kinetic friction. And we have also introduced the fact that at equilibrium, if you have a system, we are going to consider friction in it. We can add the friction equation, which is the friction force equal to mu multiplied by n, where mu is the friction coefficient and n is the normal force. In this video, we are going to present the steps we are going to be using in order to construct the equations of equilibrium for a static system, and also solve an example to show how we are going to use friction in our static problems. Let's start with talking about the steps involved in equilibrium problem where we are going to consider dry friction. Again, dry here means that we are not going to use lubricant liquids between the surfaces of the object and also the other material that it could slide or slip on top of. So what are those steps? So step one would be drawing necessary free body diagram, which is actually it's a practice that we should have now been familiar with. So the free body diagram is very important, and as we mentioned in the previous video, the friction force is going to be equal and opposite in direction to P, which is the pulling or the active force. So we're going to look very carefully on actually how we're going to place friction force and add it to our free body diagram that we learned how to construct. So we want to make sure that we show the friction force in the correct direction, which is always opposite to the motion or impending motion. Second step, we would like to determine the number of unknowns. We are usually in statics problems. So far, we were able to solve up to 3 unknowns, and that is because of the fact that we are using 3 equations of equilibrium: summation of forces on the x-axis equal to 0, summation of forces on the y-axis equal to 0, and summation of moment around a particular point equal to 0. Here at this moment, we're going to use also another formula, which is the friction force equals mu multiplied by n, and again mu is the coefficient of friction and n is the normal force. However, do not assume that F equals mu s multiplied by n unless the question is stating we have impending motion condition, right? Once we have this condition, it means that I can use mu s, which is the static coefficient of friction. It's very important. So we will going to show how we're going to use it in a problem. So we are going to add a fourth equation where F equals mu multiplied by n, and now I have a set of 4 equations where I can solve for up to 4 unknowns. The third step is to apply the equations of equilibrium and appropriate frictional equation to solve for unknown, and this is what I meant by constructing 4 equations of equilibrium to use. Now, let's go into an example and see how we're going to construct our equations of equilibrium and use it to solve for unknowns. So in this example here, we have an automobile that has a mass of 2,000 kilograms, and we are assuming that we have a coefficient of static equilibrium of 0.3. Again, this is static equilibrium. So the question said, find the smallest magnitude of F required to move the car. When we say the smallest magnitude of F required to move the car, so we are about to move, almost going to move, and we are going to assume if the back brakes are locked and the front wheels are free to roll. Those are our conditions. So smallest magnitude of F required to move the car means that I can use mu s. So I'm about to move. And if you recall our graph, which we have P and we have the friction force, we have something like this, right? So about to move, this is the static friction force, so I can use F equals mu s multiplied by n in my equations of equilibrium. So what is the plan to solve this problem? First, we need to draw the free body diagram of the car, and that's what we're going to be doing. And we need to determine the unknowns. We should be able to, if we are considering friction, we should be able to, build and construct 4 equations of equilibrium that can allow us to solve for 4 unknowns. Keep that in mind. Also, we'll apply the equations of equilibrium and the friction equations to solve for the unknowns, and that which I mentioned that we can solve for up to 4. So a quick, if I want to draw this free body diagram here on this image quickly, so we have this force, external force, that is acting on that direction with a 30 degrees angle with the horizon, and also we have wheels from the front and the back, and I'm going to assume that we have symmetry, so I'm going to use it, solve it as a two-dimensional problem. So the first thing to do is that this is my center of gravity. I'm going to put the weight actually in the center of gravity, and I'm going to do that W equals 2000 kilograms multiplied by 9.81, and that's my weight in newtons, right? I'm going to, since we have friction on the surface, we said that if the back brakes are locked, then mean that I have a friction force here, right? And if I'm pulling, that's the direction of the motion to that side, that's how it's going to be moving. The friction force should be on the opposite direction, so I'm going to call this friction B, the point B. And also I should have a normal force at B. I'm going to call that NB. The front wheels, we said the front wheels are free to roll, so we don't have friction here. The only force we can think of is the normal force, and I'm going to call it NA. So if you look at the system that we have, I have a force NA that's unknown, that's 1. NB is unknown, that's 2. I have friction force, that's 3. And I have a F that's unknown. So I have 4 unknowns, which I can solve for because I can add the friction equation. Let's see how this is going to be unfolding. From the previous slide, I have my force. This is the acting force. I have a normal force at A, a normal force at B, and the friction force at B. And we have the weight, which is 2000 kilograms multiplied by the gravitational acceleration, 9.81. And this is your free body diagram. So don't be intimidated by what we are analyzing. It's all about putting the right forces in where they should be, and with the normal forces and the friction forces, and it should be good. This is my free body diagram, and that checks. I need to construct now the equations of equilibrium in order to solve for the unknowns. Remember, we have 1, 2, 3, 4 unknowns, so I need to construct 4 equations of equilibrium. So what are these equations? So the first thing that we look for, so those are our unknowns, those are the equations. So if we did the forces, summation of forces on the x-axis equal to 0, we know that we are just going to assume that going to the right is positive. In the positive x-axis, I have minus. So if we are assuming that's positive, so FB is going to the right, that's positive, the friction force. F, I can resolve it into 2 components. I will have here the x component F cosine 30, and the y component is going to be F sine 30. So the force on the x-axis, the negative x-axis, is F cosine 30, and that's this one, and that's your first equation that we were able to construct. The y-axis, you have NA going up, that's assuming it's positive, NB going up, that's positive. I have also a positive F sine 30 again, and also I have a negative 19,620, and that's the multiplication of 2000 multiplied by 9.81. That's 19620 newtons. So there you go. We have the second equation, that is summation of forces on the y-axis equal to 0. Now let's do the moment. We're going to select the moment at point A. Recall that we said that we need to find the moment, the point where it has the largest number of unknown. So you can select this one, or you can select the B. It's either one, and that's the reason why I can select A or B, is that this FB is passing through A, so that's also going to be cancelled if I want to measure the moment around A. So let's select A. If we do the moment around point A, so NA is now going to contribute to my moment. FB is not going to contribute to my moment. And so let's look at the other forces. So the first force is this one here, which is, this is the line of action of the F cosine 30. Remember that we have this 0.3 distance. It's a small one, but it's still a distance. So if I'm assuming counterclockwise to be positive, this force is going to move counterclockwise, so that's positive F cosine 30, and the distance is 0.3. How about the sine 30? F sine 30 is going to, this is the distance between F sine 30 and A, which is 0.75, and it's going to rotate clockwise, so that's negative. You multiply the force with the distance, you get your moment. So I'm done with these two forces. Let's do now NB. NB is going to rotate counterclockwise, so that's positive, and the distance between A and the line of action of B is 1 plus 1.5, that's 2.5. And the last thing is the weight. So the weight is going to rotate clockwise, so that's negative, and the distance between the line of action of the weight, which is 1 meter multiplied by 19,620, and that is your moment. So those are three equations. Now I need to construct the fourth equation, which is the friction equation. So assume that the rear wheels are on the verge to slip. That's what we assumed actually, because we want to ask for the minimum force. So thus FB, the force, the friction force, which is a static friction force, equals mu(s), which is the coefficient static friction, the coefficient of static friction, and NB is the normal force going up. So this is my fourth equation. 0.3 is my mu(s), given from the question before. So I have now four equations with four unknowns that I can solve. All what you need now, what you need to do is to substitute each, one in a couple of equations, and then you will find the unknowns. You can use your calculator as well to do so. So summation forces on the x-axis equal to 0, summation forces on the y-axis equal to 0, summation of moment around the point should equal to 0, and then I have the friction force equals mu multiplied by n, and this is my fourth equation. And now I can analyze the system and find all the unknowns as mentioned in the system. If you do the analysis and solve the equations from 1 to 4, those are the values that you come up with. So please double check that this is what you are getting. And that concludes our video, in which we talked about the steps to solve a system as a static equilibrium, and in which we included and counted for friction, and we solved an example in doing so. Keep in mind that we are doing the same thing since the beginning of the semester when we are analyzing static systems, is that we want to add the forces on a free body diagram and then construct the equations of equilibrium and then solve them. This is the last type of forces we were able to add, which is the friction force, and it allowed us to add another equation to the system of equations of equilibrium that we can solve, and it allowed us to solve for now another unknown. So instead of solving for 3 unknowns, now we can solve for up to 4 unknowns using the friction equation. Thank you for watching. Until the next video. Bye.